Hello everyone. Welcome to this lecture on entropy. In general, entropy is a measure of uncertainty, disorder, or randomness in a system. If the uncertainty or the disorder or randomness is high, we say it has a high entropy. The concept appears in several fields such as thermodynamics, statistics, machine learning, data analysis, data sciences, and ecology. So let us look at a few examples, one from each field or each area. Right. In thermodynamics, for example, if we consider some ice melting situation, suppose ice melts into water at room temperature. So if you consider the ice state, in solid ice, water molecules are arranged in an ordered structure. Right? There is no randomness that much. Molecules don't have the freedom to move in that case. But after melting, the molecules move more freely and becomes less ordered, and freedom of movement increases. So when ice melts into water, that results in increase in entropy of ice water system. Right? So when it becomes more free or more random, the entropy increases. If you look at an example in statistics, for example, let's look at the probability of a die. Consider two dice with different probability distributions, right, of getting the numbers from 1 to 6. If you consider a fair die, each side has equal probability. So probability of getting 1, 2, 3, 4, 5, 6 separately are equal to 1 over 6. So since all outcomes are equally likely, the result of the roll is highly uncertain. So once we cannot say with a high precision, if you roll the die, which number we are going to get. So there's a high uncertainty is high there. Therefore, the entropy of the probability distribution of this die, of a fair die, is high. On the other hand, if you consider a dice with, say, one or two sides have high probability than the other ones, like suppose probability of getting 6 is 0.75 and probability of getting all the other sides have equal probability so that they each have to have 0.05 probability. So if you roll this kind of dice, you can predict the outcome with a very high precision, very high probability, very high accuracy, right? So here the freedom or the randomness is less, therefore, right? Since the outcome 6 occurs most of the time, the result of the roll becomes much more predictable. Therefore, the entropy of the probability distribution of the dice outcomes is low here, right? So in this context, entropy measures the uncertainty or randomness in the probability distribution of the die outcomes. So we are considering the randomness of the probability distribution. Okay. So let's look at another example that may be an application of machine learning, an example of a decision tree. In classification problems, entropy measures impurity in data. Suppose a data set contains, uh, for some question, the answer has been one of the three things, where one answer is yes, the other one is no, the other one is no, maybe. But suppose two of them have roughly equal probability, but one is less, right? 50%, 40%, and 10%. But in this case, since the observations are distributed among several classes, the class membership is uncertain to some extent, right? Even though two of them are somewhat close, there is a high probability maybe. So at least, uh, therefore, it's difficult to predict. There's some uncertainty, high uncertainty. Therefore, the entropy is relatively high in this case. But on the other hand, suppose there are only two categories where there are 90% yeses and only 10% no's. In that case, we can see that predict, right? If you look at, if somebody asks you to predict the next observation that you got, there's a high probability that the next one will be yes. So therefore, uh, the entropy there is less. So that's the situation in a data set. If you look at the possibilities in decision trees, right? So then the class membership, right there, which to which class an observation goes, the class membership is much more predictable in the second case, right? In the second data set. Therefore, the entropy becomes much lower because the uncertainty in the classification is greatly reduced there, right? Okay. Let's look at an example, possible example in data science. Customer purchasing behavior. Let's consider again two customers. We suppose we have records of customers. Uh, Suppose an online store studies the purchasing patterns of two customers over a long period. So this person's data are available for a long period because nowadays the telephone number and everything is recorded. Usually they have this loyalty, this thing, and therefore they record those things. Therefore, it's easy to uh, follow the pattern, right? Suppose customer A usually purchases groceries, household incomes, and other products with these proportions, right? 85% of the time groceries, 10% of the time household items, and 5% of the time other products. So since most purchases belong to one category, the purchasing behavior is fairly predictable in this case, right? For that person, purchasing behavior is very predictable. Therefore, the entropy of the customer's purchasing is very low for that person. On the other hand, if there is a customer whose probabilities are distributed very much around several categories of items like groceries, clothing, electronics, books, and sports items, and then each have some small probability so that the total will be equal to one, or the percentage should be equal to one, then it's difficult to predict what the next purchase will be. So there's a high uncertainty, and therefore for that customer, the entropy is high. Since purchases are spread across many categories, the purchasing behavior is less predictable. Therefore, the entropy of the customer's purchasing pattern is relatively higher than that of the customer A. So entropy helps data scientists measure behavioral diversity and unpredictability of customer data, right? Usually, based on these things, data scientists can do a lot of things. So this entropy is a helpful measure as they are predictable. Let's look at an example of ecology and biology. In this case, we are considering biodiversity. Suppose two forests are studied with respect to the distribution of species in those two forests. Suppose in forest A, there are many species with fairly similar population sizes, right? We know that these have been, of course, obtained and observed using some data. So suppose they have found out that there are five species, each with some small probabilities, similar, roughly similar, but small, right? Because they have got up to 100 nodes or anything. So they will naturally be small, but roughly equal. Therefore, it's very difficult to predict anything here about the species. Suppose, for example, you are predicting the next species that you are going to find in an experiment, right? So it's difficult to predict the next species, what the next species will be that you will find. Since the species population are distributed fairly, evenly, the species of the next randomly selected organism is difficult to predict. Therefore, the entropy of species distribution is relatively high in forest A. On the other hand, suppose in forest B, there is a one species dominating species A, 85%, all the others are very small, uh, might be similar, but in this case, the next species that you will find is predictable with a high probability, high precision. That would be species A. So there is a less uh, freedom or less uncertainty, and therefore less uh, entropy. Right? Since most organisms belong to the single species, the species of randomly selected organism can be predicted more easily. Therefore, the entropy of the species distribution is relatively low in this case. Okay. So those are some examples where people use the idea of entropy, right? But how do we measure this entropy, right? We just said that if the uncertainty is high, or if the disorder is high, if the freedom of movement is high, then we say it has high entropy. But of course, in order to compare, usually we need some measure, right? And that measure should have some favorable properties also, right? So what is the commonly used measure of entropy? There are two types of measures mainly used. One, if the type of variable that we are observing is discrete, is called discrete entropy. The other one is called differential entropy if the type of the variable that you're observing is continuous. So let's look at these two separately. So we first look at uh, the discrete entropy. Right. So for a discrete random variable x, suppose you are observing in each of the previous cases, we were observing some random variable. Each had some probability distribution. So if the random variable x is discrete with some, say, finite number of categories, finite number of possibilities, each category has, or each possible number has probability p1, p2, up to pn, right? In this case, the commonly used entropy, denoted by this curly E here, is calculated as negative summation of pi times log pi, right? Pi's are the probabilities that any observation of x will be in category I. Oh. So the measure is defined as negative I from 1 to n summation pi times log pi. But if you look at this quantity statistically in terms of relative to this random variable, Uh, this is actually, you can first try see that this is the log pi is the probability that x is equal to xi, right? So this is the probability mass function of x evaluated at xi. This simple pi is equal to p of x. It should have been is better, I think, if I wrote it as in the usual notation here. If I wrote down a subscript capital X here, right? So this whole thing is this pi part, right? So that's the probability mass function of X evaluated at Xi, right? So if you look at this quantity now, you can easily understand that this is actually the expected value of negative of expected value of log px. So again, you can write down px evaluated at this random variable x. So this is now here we are evaluating px at simple xi, but when you consider the expected value, you can see this whole thing is a negative expected value of this random variable, right? So because you know that expected value of g of x, right? If x is discrete and if you have only finite number of possibilities for x in this case like this, so this is equal to I from 1 to n uh, g of xi times pi, right? Pi will be the probability that x is equal to xi. So it's like that. Now in this case, gx is equal to log uh, px, right? So therefore, it's easy to see that this is the expected, negative expected value of log of px. So that is the definition of a discrete entropy when you're considering a random variable with finite number of possibilities. Discrete random variable with finite number of possibilities. And then let's look at the properties of this quantity. Now, each pi is a number between 0 and 1. So therefore, log pi is going to be a negative value less than or equal to 0, non-positive always, because when pi is between 0 and 1, log pi is less than or equal to 0. Therefore, pi times log pi will be negative of that. Negative pi times log pi is greater than or equal to 0, and hence the entropy is always greater than or equal to 0 in this case. That is for a discrete random variable. Entropy is greater than or equal to 0. Thus, the entropy of a discrete random variable is always non-negative. And this entropy was introduced by a person called Shannon. So therefore, this entropy is called the Shannon entropy. So what are the other properties? So that is the definition and the main property, positive. But in addition to that, uh, this entropy becomes zero under complete certainty, right? For example, if all the observations are in only one category, then uh, pi is equal to 100% or 1, in which pi is a probability, therefore it has to be 1, right? So in that case, uh, log p is equal to 0, therefore the entropy becomes 0. And according to this equation, if you consider this formula, that quantity increases with uh, high unpredictability, right? Unpredictability, if the unpredictability is higher, then the uh, entropy is higher, right? And this quantity is maximized if if all the probabilities are equal, that means it's distributed equally uh, among the categories, possible categories. So that's where the unpredictability becomes highest, right? For example, if you have only three categories, each category has 1/3 probability, you cannot predict. It's very difficult to predict the next observation. So that is where the maximum entropy will occur when categories have equal probabilities. But this entropy, because it's a function of p, where p is a continuous random variable, right? Continuous quantity between 0 and 1, it is entropy is a continuous quantity, behaves continuously. It is additive for independent systems. So if you want to look at the total entropy of two independent systems, the total entropy will be equal to the sum of the entropies in the two systems. And naturally measures average information content, right? So this entropy can be considered as measuring the average information in the system, right? So therefore, that's why we can consider or use it to compare the randomness in two systems, right? So now let's look at the entropy. Commonly used entropy for situations where the random variable of interest x, capital X, is continuous. Suppose x has some probability density function fx, simple fx. Then we define the entropy as negative integration of fx log fx dx. So you can see that's a direct extension of the discrete case, Shannon entropy. And you can see that actually similar to in the previous case, this is also negative expected value of log of f capital X. So it's also the expected value of f of x. In the previous situation, it was the negative expected value of log probability mass function evaluated at capital X, p x. Right. So this is called differential entropy. Differential entropy. But the main idea is the same. Of course, we cannot apply the summation here, and we don't have a probability mass function in the continuous case. So it has to be defined in terms of the density, and otherwise it's very similar, right? Both entropies are the expected value of the log of the probability mass function or the negative expected value of log of the density function. Now, we saw that uh, the entropy when the random variable is discrete is always greater than or equal to 0. And that fact is not uh, the same in this case, because in this case, the entropy also can be negative. Unlike probabilities in discrete case, probability density function, right, can be greater than 1. So probability density function can be greater than 1 or less than 1. Of course, it is greater than 0 always, greater than or equal to 0. But probability is always between 0 and 1. That's why, therefore, log pi was negative. That's why the entropy was always positive, because entropy is equal to negative summation of pi times log pi. But in this case, the density can be greater than or equal to density is always greater than or equal to 0, but it can be less than 1 or greater than 1. If it is less than 1, in that case, log f will be negative. But for some parts, right, in the density, uh, it can be positive. Therefore, for that part, actually, this will be positive. So therefore, when you take the integration of the whole range, the final answer can be negative. Right? So therefore, that property that we have for the discrete case doesn't apply here. So let's look at this example. Suppose you are considering a random variable x with uniform distribution in the interval 0 to a, where a can be any real number, right? Then the differential entropy is defined as negative integration from 0 to a. The density function is 1 over a times log of 1 over a dx. And when you simplify this, you get log a as the answer. But whether this is discrete or continuous depends on what this a is. Right? If this a is less than 1, this will be negative. Otherwise, if this a is greater than 1, this will be positive. Right? So therefore, in general, uh, it can be positive or negative. Right? If a is equal to 1, that means if the random variable has a uniform distribution in 0, 1 interval, in that case, uh, entropy is equal to log 1, which is equal to 0, right? So therefore, in general, in this case, the entropy can be greater than or 0 or less than 0, anything. Uh, so now let us look at when the maximum entropy occurs. We have already mentioned that earlier, maximum entropy occurs, especially for a discrete case, right? Maximum entropy occurs if the probabilities are distributed evenly among all the possible values, right? So in that case, what is the maximum entropy, right? So we will first show that in a discrete case, uh, maximum entropy occurs if pi's are equal, p1, p2, p3 up to pn are equal, and in that case, we can get the value of entropy. And we are going to show that this occurs if all the pi's are equal. That is, in that case, it has to be 1 over n, each probability. And in that case, of course, substituting that value into the formula, we will see that the maximum entropy in that case is log n, right? Right. So we want to maximize the entropy subject to this constraint where the sum of the pi's is equal to 1. Right? So therefore, we are maximizing some function subject to a constraint in this case. For that, actually, we can use the Lagrangian multiplier method. So we write down the Lagrangian multiplier as a function of those constants, those parameters that we are interested in, P1 up to Pn, and also there has to be a Lagrangian multiplier, lambda. So we write down this Lagrangian function. Right? This is the quantity that we want to maximize, right? And then this is the condition under which we want to maximize this thing. So therefore, in general, we write down the Lagrangian function as the quantity to maximize, or in general, it may be to minimize also, but in this case, it's a maximization, minus lambda times the constraint written as an equation. So what we do is we differentiate with respect to each parameter of interest. So then if you differentiate with respect to pi, you get this. And at the maximum, or in general, in other situation, at a minimum, it will be the first derivative has to be equal to 0, right? And we can check, of course, whether it's a maximum or minimum by looking at the second derivative. But in this case, I'm not going to do it because we already know that's going to be a maximum. If you want, you can. I invite you to check it. So when you have this, then this equation will give you pi is equal to e to the power negative 1 minus lambda. But what is lambda? In order to get the lambda at the maximum, again, we have to differentiate with respect to lambda and then get the value. So when you do that, uh, right, we get this expression. That means, oh, in this case, actually, yeah, we don't even want to get the exact expression. No. We only want to show that they all have to be equal, right? So this pi is equal to e to the power minus 1 minus lambda. This side is not changing with I. So P1 is equal to this value, P2 is equal to this value, right? And so on. So therefore, we have shown that the maximum, right? I have not shown that it is the maximum, but I invite you to check the second derivative. We can show that the maximum occurs when all the p's are equal. That means pi has to be equal to this lambda. You can get the expression for lambda in this case, right? Uh, but we don't need at this point because we are going to show that all the p's have to be equal. And if all the p's are going to be equal, and we know that this sum is going to be equal to 1, therefore each pi has to be 1 over n. So once you substitute that into the uh, entropy formula, you will get this expression, right? Maximum is equal to 1 over n, that is pi log 1 over n, and you can write down it as this and simplify this. Finally, you get log n as the maximum entropy. Therefore, the maximum entropy is attained when all outcomes are equally likely and the maximum entropy is equal to log n, right? So, as we explained in the beginning, entropy is maximum if there is a maximum uncertainty, right? Maximum uncertainty occurs because we cannot predict uh, with a high probability which category the next observation will be falling into. All the categories have the same equal probability. In that case, it's very difficult. That is where the maximum randomness, maximum entropy occurs. Right. So entropy can be used to define the efficiency of a system by comparing the observed entropy with the maximum possible entropy. So for a given situation, right, there will be a value for the entropy, but of course, then from system to system, the maximum entropy will be different depending on n, of course, in the discrete case, right? So therefore, it is better to look at the relative entropy relative to the maximum. So therefore, usually we define the efficiency of a system, right, as a relative entropy of the system relative to the maximum entropy of that system. Right? For example, consider discrete distribution with finite number of possible states. The maximum entropy occurs, as we showed in few minutes ago, when pi is equal to 1 over n, and the maximum entropy is log n. So then the relative efficiency of the system is uh, entropy of the system divided by the maximum entropy that can be obtained. And it's going to be like this, right? Sometimes it is expressed as a percentage. In that case, you have to multiply it by 100 and then say percent, right? So how do we interpret this uh, efficiency or relative entropy, right? So in that case, it's going to be between 0 and 1, right? Therefore, it's easy to compare between two systems if you want, right? So efficiency close to 1 indicates maximum randomness, 100%, 100%. That means in that case, uh, entropy of the system will be equal to the maximum entropy possible for that system, right? So it's 100% maximum randomness or maximum utilization of all possible states, right? Probabilities. All the possible states have been used equally, right? So that's where the entropy will be 1 or 100%. On the other hand, if it is close to 0, right, that indicates the system is concentrated in one or maybe only few possible states or categories. Therefore, it has lower uncertainty. That's how you can interpret this relative uh, entropy or the efficiency of the system in terms of the entropy. So this concept of efficiency used in the uh, relative entropy is used commonly in information theory, communication systems, ecology, economics, and reliability studies in various areas. Excuse me. Let's look at an example, just a simple example to understand the calculation and then interpretation. Suppose a forest contains four species of trees with probabilities like this: 40% one type of trees, 30% another type of trees, 20% another type of trees, and remaining with another type of trees. Right. So when you look at this, actually, you can see that the total probabilities have been mainly in these two categories. So let's look at what we are going to get as the relative uh, entropy or efficiency of this particular forest, right? So entropy is equal to finally 1 point. Okay. This is the entropy, 1.28, right? Entropy of this particular forest. But what is the maximum entropy if there are only four species? What is the maximum entropy? Maximum entropy is going to be log 4, log n is going to be 1.38. So therefore, we can see that the entropy of this forest is actually close to the maximum entropy, where therefore the efficiency, if you calculate, will be 0.92 or 92%. So that means it has a high efficiency. So therefore, the tree population is fairly well distributed among the four species, fairly well, right? Of course, two in uh, high probabilities, two high probabilities were in two categories, but uh, this is what you get as the efficiency in this case. The diversity is close to the maximum possible diversity. If one species was dominating almost completely in that case, entropy and efficiency would have been much smaller, right? So that is the end of that topic, entropy, right? In the book, of course, there's not this much details. So what I did was I gave you some examples in each area, and then I discuss in more lengthily than the discussion in the book. Right. So then there is one more topic that I want to discuss, an interesting probability distribution uh, in the book. It's called Benford's Law, actually. The distribution of the first digit in a, for example, in a data set for a certain random variable whose values are non-negative, right? So this particular question is about the first significant digit of the numbers appearing as observations, right? So first digit, not the value of the observation. So somebody was interested in finding out the distribution of the first digit of a set of observations which are non-negative. So Benford's law describes the distribution of the first significant digit in many positive real valued data sets. Right? Positive, they are considering positive values, you not even including zero, right? If there is a zero, then there will be no significant digit. No significant digit is the first digit which is different from zero, right? So the first significant digit means the first non-zero digit in a number when read from left to right. For example, if you consider 357, so the first significant digit is 3. For this number, first significant digit is 4. For this number, the third number, first significant digit is 8. So that is the first non-zero digit appearing when you are reading from left to right. So therefore, what are the possible values for this first significant digit? It can be 1, or it can be 2, or it can be 3, like that, up to 9. So there are 9 possible values, excluding 0. Right? So somebody was interested in finding out what is the probability. If you look at a data set, what is the probability that the first significant number is 1? First significant number of these values that you have is 1. What is the probability that the first significant number is 2, and so on? What do you think? You might think that each number has equal probability, right? That's a natural thing to uh, think, actually, right? There's somebody might think there's no reason for different numbers to have different probabilities. But of course, it was found that it is not like that. It was found that the smaller numbers have high probability to appear in as the first digit than the large numbers like 9. So let's look at this interesting problem. So one would guess that the first digit is uniformly distributed. Of course, in this case, we are looking at discrete uniform, not the continuous uniform. But surprisingly, it was found that it was not like that. It was not uniformly distributed discretely. So according to this finding, it's called the Benford's law. It's actually a probability mass function, right? According to the Benford's law, smaller digits have high probability, occur more frequently as the leading digit. Of course, this is not always true. This is true in most cases. This is not a law that is applicable for any data set. Like, there are always restrictions. Remember, we discussed in the previous uh, video that, for example, central limit theorem, law of large numbers have exceptions, right? Those theorems or those laws are not valid for all cases. Similarly, here, Benford's law is not also applicable for any data set, any positive number data set. But most of such data sets follow this law, right? So let's see how uh, to derive the probability mass function. This is somewhat interesting, but let me give you the formula first. In particular, the probability that the first digit is, for example, D. Let's denote the first digit of a randomly selected positive value to be capital D. Then we can talk about what is the probability that capital D is equal to 1, what is the probability that capital T is equal to 2, and so on. So in general, we will look at the probability that capital D is equal to simple D. So this is what this Benford's law tell you. It's going to be given by this expression, log base 10, 1 plus 1 over D. So from this equation, you can see when D increases, this quantity decreases, therefore the probability decreases, right? So that's why we said actually earlier that the smaller values have high probability, larger values have small probability. But let's see how to derive this equation. Right. Okay, this table shows the values that you get if you apply, for example, this formula for these D values. These are the actual probabilities that you can get. So looking at the probabilities also, you can see that starting with 0.3, it goes down to 0.46. That means if you randomly select a number from a set of numbers that are positive, about 30% of those numbers are ones, right? 17% of them are approximately twos as the first significant number, right? So that's what we see according to this Benford's law, right? So let's now see how to derive this equation. It's an interesting derivation. Let capital X be a positive real valued quantity. And any such number, any positive real number can be written in this form, right? M times 10 to the power some k. right? Where this m is between 1 and 10, inclusive those two numbers, right? So you might not see how it becomes like that directly. So I have looked at some examples for you. Try to take any integer or any real valued number, positive real valued number. Not necessarily an integer, it can be a decimal number also, right? So if you consider 357, you can write down it as 3.57 times 10 to the power 2, right? So in this case, m is equal to this one, that is between 1 and 10, k is 2. If you consider a decimal number like this, so you can write down this one as 4.72 times 10 to the power minus 2. So this m is again a number between 1 and 10. Of course, k can be negative also. And similarly, this number can be written as 5.2 times 10 to the power 3. Again, 5.2 is between 1 and 10. This number can be written as 8.91 times 10 to the power minus 4. This number is between 1 and 10. Right. So you can see that the first significant digit of x is determined entirely by this value m here. What is the value m? That's right. This first digit here is 8. First digit here is 5. So that is included in m here. So for example, this m here is between 1 and 10, inclusive n less than 2. Then the first digit of the number is 1. Right? If m here is greater than or equal to 2 but less than 3, then the first digit is equal to 2 and so on. Right. Now let us consider the log with base 10 of this number x, which we wrote as m times 10 to the power k. Right? Y is equal to log base 10x. Of course, we can consider this log because x is a positive number, right? So when you write down that, usually it will have a integer part and the fractional part. Right? So log x. If you consider the fractional part of log x, we are going to assume, make an assumption there. Right? The fractional part is always between 0 and 1, right? Inclusive 0. If the number is a full number, then fractional part will be 0. But fractional part will be always less than 1. So therefore, the fractional part is going to be between 0 and 1. We are going to make this assumption. So under this assumption, actually, the Benford's law has that particular density mass function. So we are going to assume that that fractional part is uniformly distributed around in the interval 0, 1, which is a fairly good assumption, the fractional part. Now let us again look at this log x term. Log x is equal to log m times 10 to the power k. So it's equal to log m plus k. So the fractional part is going to be this part here, right? The fractional part is going to be this one. Therefore, the event that the first digit is d can be written as the first digit is d if the m is between d and d plus 1, where if m is greater than or equal to d, less than d plus 1, right? Then the first significant digit will be equal to d, as we saw in the previous examples. So therefore, the probability that the first digit is equal to simple d, that is the probability that capital D is equal to simple d, can be obtained by looking at the probability of happening this event. Right? But now, because we are considering the logs, right? Because we can convert this event by considering the log of this inequality, because log is a one-to-one function. We can easily get the equivalent event. So if you take the logarithms, this event is equivalent to this event, log d greater than or equal to log m less than log d plus 1. So therefore, the probability capital D is equal to simple d is equal to that the random variable. Now we are assuming that the fractional part, after you take in the log, is in the uniform as a uniform distribution. So therefore, we are considering that what we want to find out is the probability that this quantity will be between these two values in a uniform distribution in a 0, 1 interval. Right. So therefore, probability that capital D is equal to simple D will be equal to the log M will be between these two when this quantity is uniformly distributed in the interval 0, 1. So uh, in the uniform distribution in the interval 0, 1, the probability that the quantity will be in a given range will be equal to the length of that range. So therefore, probability capital D is equal to simple D is equal to the length of that range that we are looking at, log D plus 1 minus log D, which can be written as log D plus 1 divided by D. And that's why we get this expression in the Benford's law, right? So therefore, notice that this assumption is purely based on one important assumption that log of when you take the log of x, the fractional part is uniformly distributed, which is fairly a good, reasonable assumption for most data sets, but it may not be reasonable for some particular data sets. In that case, the Benford's law will not be valid for that kind of data sets, right? So Benford's law commonly appears in naturally occurring data like population sizes, financial data, prevalence, stock market data, physical constants, and so on. So therefore, Benford's law is widely used in detecting frauds in financial data, mainly accounting, uh, auditing, and forensic data analysis, because fabricated data that may appear in that kind of situations can be obtained because those kind of fabricated data sets with those fabricated data will fail to follow the Benford's uh, proportions, Benford's law, right? Generally, we would expect if there are no frauds, that kind of data sets should follow Benford's law. But if there are fabrications, right, changed values, usually the proportions will change. Proportions that we are expecting according to the Benford's law will change significantly, and therefore we will guess that there has been some kind of changes, growths. Right. So that is the end of this lesson. Uh, in the next lesson, we will look at some problems given in the book in the chapter 2. And also we will also do some simulations to understand some of the concepts that we discussed in this video and the previous video. Right? We will look at generation of data also, and also we will look at this Benford's law with some examples. That will be the third video coming up.